We are very happy to have Sheshadhri here for the second part of his lecture today. For those of you who are not here like last time, let me introduce Sheshadhri once more. So Sheshadhri did his PhD at Princeton. He finished his PhD in 2008. After that, he did a postdoc at IBM Almaden, following which he was at Sandia Labs, Sandia National Laboratories, Livermore, after which he joined UC Santa Cruz, and where he's the full professor right now. And additionally, he's also an Amazon scholar. So Sheshadhri's research has won all kinds of awards, like Best Paper Awards in KDD, WWW, Wisdom. And I find it impressive that he's able to attack problems that are relevant in practice using tools derived from theory. And in pure theory land, he has done some seminal work in testing monotonicity, testing graph properties. And we are in for a treat today where we'll understand directed Tarragrand inequality better. So with that out of the way, please take it away, Sheshadhri.
Thanks, Akash. Thanks for the very generous introduction. And again, just like last time, please feel free to interrupt me at any point if something is not clear, and I'm happy to go over things. And again, I'll be, sort of doing this talk with pen and paper, so there's a lot of flexibility in covering, whatever interests the crowd. So what I'll do is maybe I'll spend the first 10 or 15 minutes just going over what we did last time, a quick summary, and then we can go into the details of the directed Talleyrand inequality proof. And I think that with the right with all the notations set up, I hope to be able to show you sort of essentially the guts of the proof, not in a way that I think it should be fairly clear. Hopefully all the details, there are some details, but I think I can show the main idea, at which point most of you would be able to work it out yourself. So with that, let's get started. So, just to remind you, the directed Talleyrand inequality is sort of the main tool to get these O of root D monotonicity testers. And the result, as proven by Court-Minzer and Safra, is this directed Talleyrand inequality. What it says is that it's an isoperimetric inequality where you have some notion of directed volume and some notion of directed surface area, and you say surface area is at least volume. So the volume, and this is sort of a surprise, the volume is the distance to monotonicity. It seems like a bizarre notion for a directed volume. The measure of surface area is also bizarre in its own sense. So what it says is, so I'm sort of abusing notation here. I'm just saying take the expectation over all points, but I'm only going to count this function over where the value is 1. So one way to look at it is that I'm averaging over all the points, but I'm only going to count influence over points where the value is 1. So what is inf plus of x? So for any point 1, you look at the number of violating edges that are going upwards, right? Because in this hypercube, all the violating edges are going upwards. So the influence is only counted from 1 to 0. So that is the inf plus of x. The degree is that sort of directed upwards degree, and the square root of that. So you look at the expected square root, and this is at least the volume. Now, where did this sort of square root come up, and where did this overall picture come up? Well, so Talleyrand in 93, in the analysis of Boolean functions, proved a seemingly, a similar statement, except in the undirected sense. So in the undirected sense, we have variance, which is the measure of volume. And we're just looking at, the total influence, which is, you're looking at the influence that goes below or above or anything. And so just to, motivate this, if we look at the directed Talleyrand inequality, which is what we'll focus on, and let's just assume that the distance to monotonicity is going to be a half or some constant. So in this setting, the two sort of typical functions one looks at are the dictator function and the anti-majority function. So in the dictator function, all the influence values are 1. So we're again just counting it at the 1 valued points. And so the degree is just 1, because every vertex on the one side has exactly 1 violating edge, right, which corresponds to that dictator coefficient. And so there are 2 to the d minus 1 points, each of which has an influence of 1. So the expectation of the square root is is basically theta of 1. Now, what's interesting is if you look at anti-majority, so I'm looking at the opposite of majority because I'm looking at functions that are far from monotone. The only points that actually have any non-trivial influence sit at the boundary, which are only a 1 over root d fraction of the points. On the other hand, all of those points have a violation degree of d, because every edge, well, half the edges incident to that are going upwards and going from the 1s to the 0s. And you took the square root of that, and again, the square root d cancels with the square root d, and again, you get theta of 1. And just to point out, and Talleyrand's inequality sort of says that, so it's tight in both of these cases. And if you, think about it, even if you took a majority on any subset of coordinates, you'll basically get, you'll get the same tight result. I just want to point out that a lot of classic isoperimetric inequalities, for example, Poincare, the Margulis inequality, are all derivable from Talleyrand with like just a couple of steps. And just as a comment, you can also derive, for example, Harper's bound, which says the vertex boundary of any set of size theta of 2 to the d is omega of 2 to the d divided by root d. So you can derive this from Talleyrand. So it's a powerful isoperimetric statement. And in the context of monotonicity testing, it turns out there is a directed version, which is the centerpiece of this celebrated Courtmanzer-Safra result. And I'll also mention that the directed result implies the undirected one. There's a notion of robustness that, maybe we can talk about later if we have time. The main consequence that I want to point out of the robust version of Talleyrand inequality says that the boundary always, I should say, contains a regular bipartite graph. So remarkably, if you look at both of these examples, the dictator and the anti-majority, the boundary is a regular bipartite graph. And it's exactly regular. What Talleyrand essentially implies, the directed Talleyrand implies, the directed robust Talleyrand inequality implies, and you need this notion of robustness here, but keeping that definition aside, the consequence is the boundary always contains a regular bipartite graph with sort of the most optimal parameters you could hope for. And so that's very surprising that should be true. Right, and the magic of this is, that it doesn't depend on the degree, it doesn't depend on the influences, nothing. All it says is as long as you have distance to monotonicity at least constant, so directed volume at least constant, the boundary will contain a regular bipartite graph. Now I'm fudging a bit over here, but essentially, and we can talk about the fudge later on, but this is the sort of the right intuition to have. And so the whole game is, we wanted to understand how to prove this inequality. And so the idea is to sort of reduce the directed version to the undirected version. So in the undirected version, which we know from Talleyrand's 93 result, is that for any function g, any Boolean function, this expected root of influence is at least the variance of g. So we're going to try to move a directed function to an undirected function and sort of play this game. So the initial intuition is to say that we're going to construct some function g such that we can relate the directed boundary of f to the undirected boundary of g. Then we go ahead and apply Talleyrand. So we'll basically lower bound by the variance of g. And then we have to relate the variance of g to the distance to monotonicity of f. So this is sort of like, very high level. This was the aim. And we're going to pull this off, but not with 1g, but rather a distribution on g. If I'm going too fast, and if there are any questions, please stop me. Now, one of the central things to this argument is something called the switching procedure. So what is the switching operation? The switching operation starts with a function that is not monotone, converts it to a monotone function. And it does it in sort of the obvious way possible. In any dimension, it's an operator that if it finds an edge that is a violation to monotonicity, so if it's a 1, 0, it switches it to give you a 0, 1. That's what it does on all the edges. So this is the operator script S1. So for any dimension, I can define the switch operator in that dimension. One of the original results of the seminal result of Goldreich et al. Shows that you can apply the switch operator in each dimension, and you will never create violations in previous dimensions. So if you apply the switch operators in order, you end up with a monotone function. Okay. So let me now introduce this notion of the tracker function, which is like the key construct that is used in the KMS proof. So I'll, just a minor point, I'll point out that this presentation of the proof is different from the KMS proof. This is the presentation that Hadley, Deeparnab, and I came up with in trying to understand their proof, and that presentation was able to generalize to the hypergrids. So what is the tracker function? So one way to think about it is, you start with some function on the hypercube. Now imagine constructing all possible switches of this function. So you switch this function in dimension 1, you switch it in dimension 2, and then you switch it in dimensions 1 and 2. Now, this came up last time. The order of switching does matter. But what I'm going to think about is that I'm fixing the order of the coordinates. And when I'm thinking of switching on a subset, I'm actually switching on a fixed list of that subset. So I'm fudging a bit when I say subset. It's really a list. But I promise you that this is not going to create any problems. So I'm going to take the original function, switch it on 1, take the original function, switch it on 2. So that's what this circular function means. When I say S circ F, it's the function obtained by switching on the coordinates of the set in order. And then I can, switch on 1 and 2. I'm going to take all of these 4 functions and kind of put them together in this particular way. So instead of this, one can think of as like a primal view. I look at the domain, I look at a function, then I apply an operator, I get a function, look at an operator, I get a function. What if I switched my view and instead fixed a point and just look at what happened at that point? So if you look at, I'm going to construct 4 functions, g00, g10, g01, g11. Each function corresponds to a different point. So this g00 is basically looking at what happens at this point 00 over all the switches. So one way to look at this is, use some colors here, is that the original function is the red part, because this is like the 0 subset. The green function, the green one, is this. So let me put it in color so that you can see. The green function is what's here. So this is the red function, which I've put in red. Then the blue function is switching on 2, which I have over here. And finally, I have another function, which is the orange function, which is this. So I've taken these 4 functions, except I've carved them out separately. And this is sort of, one way to think of it is like, it's kind of like a duality. So I have 2 to the d functions, each corresponding to a point. Any questions about the tracker function? So should I continue? Yes.
So the list part is something that's confusing me a bit, that I take some subset S and a process subset S in that order. Is that not relevant? I did not fully catch that.
No, so you have to fix the order. So you are fixing the coordinates, you're labeling the coordinates 1, 2, 3 up to D.
Mm-hmm.
And when you switch on the subset, you have to process them in that order.
I see.
And this we're going to decide once in advance that we're going to process in that order.
So for instance, if the subset S is size 3 and D is large, then I get 8 functions? If the subset,
say it again.
If the subset capital...
No. So for a given subset, there is only one function. So fix the order. So you are calling the coordinates 1, 2, 3, 4 up to D. Let's say your subset was the element 2, 4, and 8, or 2, 4, and 5. What does it mean to switch on the set 2, 4, 5? It means switch on 2, switch on 4, switch on 5. That's what it means.
All right.
You do not permute. So in some sense, the coordinates are not symmetric. They're special. Like the first coordinate comes before the second, which comes before the third, so on and so forth.
I see. Okay. I get it.
So this is the point. Like, what we're doing is in some sense, we're not letting the coordinates be symmetric because the switching function annoyingly, is not commutative.
Right.
So you cannot commute the switching operator. So you have to fix the order in advance. This does seem a bit confusing because I'm referring to this as a subset, not a list. But you will see in my definitions, there is no loss of consistency.
Good. I get it. Yeah. Thank you.
So I think I suppose the importance is that for every S, you use the same total order.
Exactly. So there is a global consistency that I have imposed before this whole process has started, and I have to follow that. Any other questions? All right. So the main inequality that we're going to prove, this was the red box that we talked about last time, is to say that the expected, this directed Talleyrand objective is greater than or equal to the expectation. Okay, so I've written this a little bit more cleanly, so I'm going to show you the more clean version. Written more clean version here. So what I'm looking at is I'm looking at the directed Talleyrand objective of the original function, which I'm going to relate to the undirected Talleyrand objectives of these four functions. So I'm saying that the expectation of the square root of the directed influence is at least the expectation over x, which means the expectation over x is the expectation over these functions. For each function, I am now computing the directed Talleyrand objective of that function. Now observe that the function gx. Yes?
Sorry. So the way you say it, I can understand. The way you write it, I'm a bit confused.
Okay. Let me write something here and then you tell me if this makes sense then.
Sure.
So think of this function as defined on all subsets as S circ f evaluated at x. This is the function. So what does this influence really mean? So this influence, as I've written here, is saying the influence of this function gx at a set x, a set S. So remember, the set is now a domain point for this function, because in this function, if you look at these colors correspond to subsets of coordinates. So what does this influence, for example, mean? What's a good example? So let's look at this point, for example. So what is this point saying? So this is the function g10 at the set 2. Now this point has influence because this edge is influential. So this is the influence of this edge is simply saying that if I were to, this is not equal to g10 of 1, 2. That's what this edge means. So therefore this point has influence when this fact is true, which means that in addition to 2, if I also switched on 1, the value would have changed. Similarly, you can look at this point here, where now this has influence on both these sides, because this is saying this g10 at the set 2 has influence 2, because this is saying that this is not equal to g10 of the null set, and this is also,
this is G01, right? You're looking at G01.
my apology, G01, I'm sorry, G01, thank you, G01, and this is not equal to G01 on the whole set. So G01 of 2, the set 2, is not equal to G01 of the null set, is not equal to G01 of the wholes of the 1 and 2. That's what influence means. Does this answer questions?
Yeah, this is
Yeah,
correct.
So you have essentially you have an instance for every point.
Yes.
So the instance is defined by all the subsets.
The instance is defined by all the subsets, right? So the domain of this
And
function are all
so you want,
subsets.
and you want to keep these separate. That's the.
Yeah, I want to
And
keep
then,
each of these separate. So this is like a window into what happens on this point. So it's almost like I'm just zeroing in what happens on this point as I'm doing all the switches.
yeah, got it.
So it's, I guess a dual is the way that I like to think about it. It's
No,
like
this
there
is
is,
like, yeah, there is, this is like whatever point hyperplane duality type thing. You sort of
yeah, it
change
feels
that.
like that.
I mean, somewhat, okay, not quite.
Something like that. Yeah, yeah. Any other questions? Okay. So let's actually see how this beast is proven. This is where all the hard work lies. So the proof, it's kind of, I think the main hurdle is this notational hurdle. And once you kind of like get around it and have the right pictures, the math itself is not that complicated. Okay, so let's go ahead and let's take it slow, and I think we can hopefully figure everything out. So I want to sort of essentially the argument is what we will call the hybrid function argument. So the way the hybrid function argument works is really it's going to go in phases. And so imagine in the ith phase, we compute S circ F for all subsets of first I coordinates. So imagine that you've just gone ahead and you've done this computation. So the picture that I want to draw is, so let's just think of this as the original function f, and here are all the tracker functions. These are all the tracker functions. The tracker functions g of x. So what this really means, you can think of as like we've already computed all of these values for these functions, because we have computed essentially gx of s for all subsets of I. We've computed everything here, but we have not switched any coordinate more than I. So if you look at sort of what has happened in F, everything above I, this is still potentially, this has been not switched. I mean, this is sort of a picture which is a little imperfect because after all, I'm drawing in 2 dimensions and I'm dealing with d dimensions. But intuitively, the way to think about it is in the ith phase, you have computed all of these functions. So you've switched on all subsets. So you've computed some portion of the tracker function. And there is some portion of f that is still non-monotone. So the way to think of it is in the ith phase, in all of the coordinates less than I will track influence here. In coordinates more than I will track influence here. It's kind of a weird thing. So this is where it's a hybrid function. So I'm going to write down a sort of long, unwieldy expression. But the picture that you should have in mind is for some coordinates, we're going to track the influence here in the undirected sense. In other coordinates, we're going to track the influence here in the directed sense. And this I is basically going to shift coordinates from one to the other. So let me write this down. So I'm going to define a particular potential. So my potential, which I will refer to as, lambda I. This is the potential of the ith phase. This is a long, sort of somewhat complex expression, but once we parse it, I think we'll understand what's going on. So I'm going to expectation over all x, just like standard sort of Talleyrand. I'm going to look at all subsets of the first I coordinates. Okay. And now I'm going to compute the influence in this hybrid sense. So for all coordinates, so I'm going to write the influence of gx of s colon at most I. So what this means is that the influence on coordinates. So instead of looking at the total influence, I'm only looking at the influence in the coordinates that I've already processed at this stage. For all the remaining, I'm going to look at the influence in the directed sense. So this is, let me write this down and then we'll talk through it. I'm going to do S circ F. So it's like I picked a random point, I picked a random set. So I'm looking at the expectation of the influence here. That's what this picture would give you. If you ignore this part, this is looking exactly like the undirected Talleyrand objective. Except I'm going to add on this thing where I'm looking at the directed influence in the function which has been switched on S. I'm looking at this in all the coordinates that are greater than or equal to I. Okay, so what is this? What is this really saying? It's saying, imagine if you kind of looked at just this, where I is going up to D, this is just your undirected Talleyrand objective. If you looked at this, where I is like 0, this is the directed Talleyrand objective. And this is some kind of a hybrid. It's a mix of both of these things. I'll pause for a bit. Let's stare at this expression a bit, because there are lots of this x's. So x and s are kind of, they're almost like switched here. So here it's indexing, x is indexing the function, s is indexing the domain. Here, s is indexing the function that we're looking at, and x is indexing the domain. Right, so one way to look at this is you've computed all of these functions. So there are two ways of looking at it. One way is you've computed some portion of the tracker function, but the other way is just that you've computed all of these functions for all different s's. You've computed the function. So this is like the primal view. This is the dual view. I'll write this order. This is like a primal, and this is like a dual. I mean, I'm abusing notation here. There's no like, linear programming duality or any kind of, but it's like that. The primal view says you're just looking at the function as you're doing all the switches. And so you're looking at like a primal objective. In the dual, what you're doing is you're actually looking at these tracker functions, and then you're looking at the influence here. This expression sort of makes sense. Any questions? Okay, so I'll take the silence as a sign that I can move on. So this is your potential. And as you may imagine, that the main theorem simply says that the potential continuously decreases. So just to, sort of round out the meaning of this, let's look at what this potential is at 0. Okay, so when I is equal to 0, then this term completely disappears. This is the only term that's left. And when I is equal to 0, you're looking at the total influence. When I is equal to 0, you're not even looking at any subsets. So there is no switching happening. So when I is equal to 0, you're simply looking at the expectation of x over the square root of the influence of f at x, which is, the directed Talleyrand on f. When you look at this at D, again, unsurprisingly, at D, the second term disappears. There's nothing there. You're looking at everything over here, and you're looking at all possible subsets. So you're looking at the expectation of x, the expectation of S, it's a subset of all coordinates of the square root of just the standard vanilla influence on S, right? So this is like the undirected influence on that function, on that tracker function. Okay, so any questions? Is this clear? If anything is unclear at this point, this is a good time to ask.
This is good.
Okay, all right. Okay, so let us now go into how we're actually going to prove this. And we'll see like a lot of the aspects of switching and square roots are going to start up, they're going to appear over here. Okay, so what we'll do is we'll fix X and fix S, a subset of I minus 1, because I want to prove this here. So remember, this is like a double summation over X and S. So let me look at, and let me just write, what do I have in the LHS? So, okay, so I'm going to draw a few things. So please bear with me. So this is X. Now let me look at Y, which is just X plus, the ith coordinate. I'm using notation, technically X plus EI. So let's just say that X such that Xi is equal to 0. So the ith coordinate is 0. So I look at X and then I flip the ith bit to get Y. I'm going to track the terms for X and Y together for a given S. And this is going to be important. So in the LHS, what you have is, I'm just going to write this down. You have the influence of Gx at S less than or equal to I minus 1. So bear with me as I write this expression. The influence of S circ F at X greater than I. Right, so I wrote this like long winded expression, and the influence of Gy of S I minus 1 plus the influence of S circ F of Y and I. So this is, all I'm doing is I'm saying I'm looking at this expression for I minus 1 and saying, okay, I look at a term for X and S, fix S, and I also look at what happens when I flip the ith bit. So I'm just going to keep those two terms together. Observe that if I take an expectation over all X and all S, then I just get this back. Okay, so this is what I get in the left hand side, which is corresponding to lambda I minus 1. Now, if I look at the right hand side, which is now I correspond to lambda I get a term for X, I get a term for Y, as before, but also this set S has now become like, so think of it as, in terms of this process, the ith phase, I'm looking at all subsets of I. Those subsets of I can contain I or not contain I. That's like an additional choice, right? It's just I'm generating all subsets. So I look at all subsets less than I, less than up to I minus 1, and then I can decide to add the ith element or not add it, which means I can decide to switch on the ith coordinate or don't switch. So I have a choice, and I'm doing it sort of with probability half, right? Because I'm taking an expectation over all subsets. So let me write down, it's a long expression, but I promise you that, like, I'm just doing it so that everything will be sort of pretty clear. In the right hand side, the corresponding terms that I get is I get a half because I switch on the ith coordinate or I don't. What I can do is I'll get the influence of Gx of S less than I plus the influence of S circ F on X at least I plus 1. So I'm note that now I've switched, I'm moving from I to I plus I minus 1 to I. right? Because that's basically what I'm doing when I'm moving to the next potential. So I get a term for x, I get a term for y, just as before. So let me write this down. I'm sorry, y. So this is fine. This is saying don't switch on I. Then what I'm going to get is I'm going to get a term where I actually do switch on I. So it's influence gx s plus I. I look at the at most, and I get s plus I circ f, and again I get x at least I plus 1. And let me write this down and we'll just talk through it. I promise you it's not that bad, even though it looks pretty awful. And the influence of s plus I circ f of y at least I plus 1. Okay, so maybe I'll try to zoom out a little bit and then we'll just stare at this a bit. So all I'm saying is you started at an x and a set. So you have one term. I'm also going to consider the term that I get when I add the ith coordinate to x. So I look at x where xi is 0 and I look at the thing where xi is 1, and that gives me the x and the y. Right? These are just these 2 points here. So over here, when s is a fixed set, this is pretty clear. Now what I do is I say, well, if I'm going from the I minus 1 to the next step, if I take any subset of I minus 1, I get two sets, right? I can either decide to add the ith coordinate or not. And each of them is like a half probability because I'm taking an expectation. So I'm going to get a term for x without switching on the ith coordinate, for y without switching on the ith coordinate. That's what these are. Don't switch on I. Then I get a term for x, switch on the ith coordinate, y, switch on the ith coordinate. And when I switch on the ith coordinate, I have to consider it both here and here, right? So because it's like this primal dual, right? Either I'm looking at the domain or I'm looking at the indexing of the function. So this is almost like basically just a syntactic plugging in, but that's the intuition. So is this this kind of clear? Any questions about this? If you're lost, I can go over it again. Just getting into the guts of where things are happening.
So can you say again this notation s less than equal to I?
Yes, this thing.
Yes.
So this is just saying that you are counting the influence on coordinates at most I. Like the first I coordinates, you're counting the influence in the tracker function. In the remaining coordinates, you're counting the influence in the original, so in the primal. So here it's like as you keep switching, you're going to do it in the dual, but in the coordinates that you have not switched, you do it in the primal.
So if s okay, s is only a subset of I.
S is only a subset of I, and I'm continuously increasing I.
So if x has like if x is all zeros, then it doesn't contribute, is it?
What do you mean? No, if x is the all zeros, so
Yeah.
again, think of x and s are like primal duals, right? So they're both independent variables. So x is the domain. S is a subset of coordinates, it's the operators.
Right.
So this is sort of like an expectation over the domain of points. This is like an expectation over the operators.
Right.
So this is the operator space, this is the domain space. So in some sense, they're both independent of each other. And here you're coupling them. You're saying that here I'm going to look at, I'm indexing the function based on the trackers, which is based on the domain. and I'm looking at like, the influence with respect to S. In the second one, I'm looking at basically the function that comes from applying the operator, but looking at the standard influence in the domain. So it's kind of like, it's almost like you're combining both the primal and the dual together into one large function, which you're analyzing here.
So just to recall, so just gx of S is just S, like the F shifted by S applied on X.
Exactly, right?
Yeah.
So this is again,
Yeah, and so the influence would be like, now if I think of this as a function of S, so this influence less than I would mean that I look at this S of F applied to X versus I take one of the coordinates which is in F and which is less than I remove it. If it is in S, I remove it, and then I look at that S prime
exactly.
shifted F X, and if they're different, then I count one.
Then you count one, right? So it's sorry, yes.
So and it's not monotone in this case. It is the undirected influence in this one.
This is just some undirected influence. Yeah, exactly. So this is like tracking whether the operators were changing the function at that point.
Yeah. Thanks.
Any other questions? All right. And so essentially, you have this sort of long list of equations. What you can argue, okay, so I'll kind of see if I can draw this out a bit. This red, and then over here, I'm going to draw the blue part. And here, it's like the green part. Essentially, what we'll prove is that the red is greater than the blue. We'll prove that the red is greater than the green. So obviously the red is at least the average then. So this implies the red is at least half of blue plus green. And then all you need to do is you just take an expectation over X, an expectation over S, and then you're done. Okay, so we need to prove these two statements. Any questions? So the first one, the red greater than blue, is actually pretty easy. It's mostly just a syntactic manipulation. It's in the red greater than green that you actually have to use the concavity of the square root. So the red greater than blue is actually straightforward. The red greater than green is where the concavity of the square root comes in. So I guess, we have about maybe 15-20 minutes left. The question is, are people comfortable enough with the notation that we should go and discuss this further?
I have like half an hour left. So,
okay. So are people comfortable enough with the notation that we can proceed forward, or should we pop back and I can just tell you more about how KMS gets the square root d, and then if time permits, we can come back to this. So because this is now into the weeds. This is really where the proof is going to start appearing. So open to suggestion.
I'm fine with either. I'm curious about red greater than green, but others, please chime in. Like Sundar, Piyush, Rohit.
Yeah, fine. Green is fine. I mean, I'm fine with the notation now.
Okay, all right. So as long as there's sort of comfort with the notation, it's a bit much to take in, but we'll do the red greater than blue because it's actually quite easy and it's useful. Just yes.
Okay, so just tell me if this is a sort of a broad the sort of view from above.
Yeah.
Which is you're taking this function, and as you switch, you're making it more and more monotone.
Yes.
And we are saying that before you start doing the switches, you look at the the distance from monotonicity, but as you make it monotone, you look at the variance, and somewhere these two are connected. Is that the...
Okay, so there is a bit of a bait and switch that I did here, is that the distance to monotonicity is not going to appear anywhere in this picture. It comes at the end where I have to relate the variance of gx to the distance to monotonicity. So here I'm purely just manipulating the Talleyrand objective.
Okay, but here, I mean, you're not sort of splitting again into variance, one part, some part of the variance and some part of the distance to monotonicity, and you're sort of, that is not going hand in hand here.
No, that is not going hand in hand here. I'm purely playing with this objective. So in some sense, my goal is to relate this objective to that distance to monotonicity. I am not doing that anywhere here. I sort of do this long-winded process, convert it to this objective in the undirected sense. That can be related to the variance by undirected Talleyrand. Then I have to relate the expected variance of these gx's back to the distance to monotonicity. And that's why I say, look, these gx's themselves are coming from the fact that if f was already monotone, all of these variances would be 0 because the switching wouldn't do anything. So the fact that f is far from monotone is the only reason why any of this is non-trivial.
Hello?
Yes.
So I suppose actually, yeah, it would not, maybe, yeah, it would not be possible to do it this way because, I mean, even if it were, one of them is the wrong one is decreasing, the right one is increasing, one of those things, right? So the distance is reducing, and
Yes.
the sort of the variance is increasing, and you want to show at the end, in fact, the variance is greater than equal to this mean.
Yeah.
Right?
So
something like that.
In some sense, even if you could show like what you were saying, in some sense, you have to relate somehow this objective to the distance to monotonicity. Right? And
no,
that
what I'm saying is this. So is decreasing.
I'm sorry, so you broke up for just a minute.
Sorry. No. Actually, what I'm saying is maybe completely irrelevant. I mean, see, as I see it, the distance to monotonicity should be reducing.
Yes.
And at the same time, the variance should be increasing. If we can relate these two quantities, then we are done. Right? The decrease here and the increase there. I mean, the delta.
Oh, I see. For the final argument, I see what you mean.
Yeah.
So actually, okay. So maybe I'll mention this and I'll come back. Interestingly, there are functions where f is far from monotone, yet this variance is very small. So there is actually an additional step one has to do. So it turns out that you cannot pull that, or it does not help to do that argument in here because there are these bad situations that actually happen for, like, I'll show you, like for fairly simple functions this happens. So you have to do a little bit more work to find the right restriction where what you said will work. But it becomes easier to sort of decouple those things and just directly argue that this is related to the distance. But yes, in some sense, what you're saying has to be true at some fundamental level. Okay, any other questions? Okay. All right. So let's do this red greater than blue, because I think it's an easy enough argument, and you'll get a better understanding of the notation. And then once we have that clear, we'll be able to do the red greater than green with there are some sort of pictures, and once those pictures are there, I think the proof should be there. Okay, so let's sort of start with this. So actually it turns out that in this case I can prove an even stronger statement. I don't even need these square roots. So just to simplify all the arguments, let's just assume that I only count influence. Recall that at one valued points for all functions. So that means that regardless of whether I'm looking at gx or this, only if the value is 1, I'm actually going to count influence. Otherwise, I'm going to count the influence as 0. And that's, that doesn't really affect anything just by a constant factor, as long as I do it consistently everywhere. Okay, so let's look at these terms. Actually, what I'm going to show you is even stronger. I'm just going to, so let's just look at the term for x and the term for x here. And you'll see that they're almost the same. I'm going to write them down side by side. Okay, so the influence gx s at most I plus the influence of s circ f x greater than I. So this is square root here. And then in the other, even if you ignore the square root, it's inf gx s less than I plus inf s circ f x greater than I plus 1. So observe that these two and these two are basically just the same thing except for a change in index. So if you look at this sum and this sum, I claim that there is only one coordinate that is playing a different role, and that coordinate is I. For all coordinates other than I, they're either counted here or here exactly in the same way. The only difference, so I'm going to put the difference over here, is in the first one, if you look at the coordinate I, I'm counting that in s circ f. At x, let me only look at the ith coordinate. And over here, I'm counting the ith coordinate as part of the first term. So the ith coordinate is different. Every other coordinate is counted exactly the same. So is this clear? Now I'm claiming that these two things are just the same thing. So let's look at what this means. So inf s circ f xi inf plus. So this is not equal to 0 if and only if you're looking at your function. So I'm looking at the function s circ f. So I've switched f on all the sets in S. So I'm looking at x and y. Remember, x, y are the ith coordinate. The value here was 1 and the value here is 0. Because this edge was influential in the directed sense. That's what this means. So what does this mean? That means if you switched, you're going to change the value. What this means is that s circ f evaluated at x is not equal to s plus I circ f evaluated at x, right? Because that's what the switching is going to do. If I switch on the ith coordinate now, remember this is the ith coordinate. If I switch on the ith coordinate, the value is going to change. But this is exactly the same thing as saying the influence of gx at s at I, the ith I coordinate influence is not equal to 0. So you see, these are exactly the same thing. Is this clear?
Yes.
Right, so these two things, the only difference is what's happening on that ith coordinate. And so you say over here, you're counting the ith coordinate in s circ f. You're looking at it in the primal. The second one, you're looking at it in the dual space. But you're tracking the same information. In the first, the fact that there is influence means that if you switch on that coordinate, you're going to change the value, which is what you're tracking here. This is where the switching and the monotonicity are getting connected in this. So over here, indeed, I've done more. What I've shown is this red term is equal to the blue term. They're exactly the same, and the same argument works for y. For every point, you get exactly the same thing. So what we'll get is actually it's not just greater than equal to. These are equal. The red and blue are exactly the same thing. Any questions? Okay. So now let me do the red is greater than the green. So we'll now coming to the stage where the right pictures should hopefully do it. So I'm going to draw the red. I'm going to draw the red as follows. So I'm going to draw a picture here and then. So I'm going to look at X and Y. So remember, this is the ith dimension. The ith dimension. So I'm going to look at the coordinates, some coordinates above and some coordinates below. These are the coordinates that are greater than equal to I plus 1. These are the coordinates that are less than equal to I minus 1. So remember, over here, this is like the primal above, and over here is the dual. So for convenience, remember, the function that I'm looking at over here is this S circ F, right? Because I have fixed an S subset of I minus 1. So I'm looking at S circ F, which is just F, and I've switched on all the coordinates in S. So I'm just going to call it H, S circ F. So above these, let me just put the values of H. So this is just saying that, like, let's say if this was the jth coordinate, I'm just looking at H of X flipped on the jth coordinate. Okay, so I'm tracking, and this you can look at, think of it as a directed influence. Below what I'm doing here is actually I'm looking at the dual. So below in this picture, so suppose if this was the kth coordinate, I'm looking at gx of S, and I'm just sort of XORing the kth coordinate out. So ek, so which is like XORing the kth coordinate. Okay, so is this picture clear? So above what I'm tracking is H, which is just S circ F. Below what I'm tracking is Gx of S circ Ek. So you can imagine just drawing this picture and plugging in these values. And once you have this, what I'm looking at here in these expressions is just the total influence over here according to this, right? Above I'm tracking the directed, below I'm tracking the sort of this, this funny dual influence here. But let's just have this picture, right? So once we have this picture, we can actually forget a lot about what it really means and just deal with the switch operator with this picture. Okay, so this is the red part, which is that. Now so this is what I'll just write this out. This is the red picture here. Now let's see what happens in the green picture. So the green picture is actually pretty much the same thing, except, okay, so I'm just going to draw this out here. Say X, Y. So now I have to look at the function S plus I circ F, because now I've actually switched on the ith coordinate. So the difference in the red and the blue, it's exactly the same thing. Gx, Gx, S, S, X, X, S circ F, S circ F. It's exactly the same. So you can do a term by term comparison. But when I look at the red and the green, now in the green, I'm looking at the influence at a different point. I'm looking at a different function. So I'm looking in red versus blue, I'm looking at the influence at the same point. I'm looking at the same function. In red versus green, I'm looking at the influence at a different point, and I'm indexing on a different function. So this is the primary challenge that we're going to see here. But once I draw these pictures, I think it should hopefully become clear. So the ith coordinate now, we're going to draw it off separately over here. So this is the ith coordinate. So what I have above is I'm looking at I circ h. This is the function. So I've switched on the ith coordinate. Over here, I'm looking exactly at, so let me sort of write these down. Okay, so I'm looking at I circ f. So I'm going to write something here and then you will understand hopefully. Gy of s. And everything below, I'm looking at gx of, so if I look down at the kth thing, I'm looking at s xor ek, but I'm additionally also switching on the ith coordinate. So one way to think of this is the picture if you have not switched on the ith coordinate. Now, if you were to switch on the ith coordinate, you would get this picture. So if you look at this and this, gy of s plus ek, and look at the corresponding thing over here, gx s plus ek plus ei. What does this mean?
Gy.
I'm sorry, gy. It's like saying that you take these things and you take these things. It's basically saying if you switched these, then you get this. So apply the switch operator on these two values. You will get these two values. So it's saying if you take this picture, you apply the switch operator and see what you get. And this difference that you got, you kind of have to track with this new coordinate here. So because h of x plus j, and I'm looking at I circ h. So what I'm saying is, if you look at this picture, this is the picture in the red picture, you can completely forget everything and just say like, look, I have some x and y, I have the differ in the ith coordinate, I have some edges above, some edges below, and I've defined some values here. Now I'm going to apply the switch operator in that ith dimension on all of these pairs because I can pair these up along the ith dimension. And I'm going to get a new picture. And that's basically the green picture. So the green picture is obtained after switching the red picture. So it's kind of weird because it's the switching operator on these two things. It's sort of, it's basically notationally you have to look through it. But essentially what this is saying is gx of some set and the ith coordinate. Which means if you're also switching on the ith coordinate, all you're doing is you're taking this point, looking at it's like sort of like ith brother, ith sibling, looking at the value there and deciding to switch or not. The only difference between gx and gy is that they're looking at x and y. So if you're looking at the picture with regard to x and the picture with regard to y, after switching, that's just saying take these pictures and see if you swap, if they need to be switched or not. Is this making sense?
It was not very transparent for me. I guess. There was some other comment. Go ahead.
So should I just think of with the same displacement from x and y? Right? So those are the things that are getting paired.
Yes. So I say that again, Piyush?
The same displacement from you take a direction from x.
Yes.
And you move from x in that direction, and move from y in that direction, and those get paired because they are exactly read by a switch on I. I mean,
exactly.
The I coordinate is flipped.
Yeah, and it's whether you're looking at this picture in the primal or the dual, it's sort of the same idea. It's just that exactly is just the displacement of x to y is along the ith coordinate. That whether you look in the primal or the dual, essentially the difference between the red and the green expressions is you can actually forget about this whole primal dual business anymore and just say that you have a star here and another star here, which are paired according to the ith dimension. Go ahead and apply the switch. and see what happens to the influences.
There's also an identity here, which is like something like gx of s plus ei is the same as s union I. Sir.
Exactly. So that's this hanging thing that I've put over here. That's just saying that if this was influential, you will track it over here. So if this was say a 1 and this was a 0, then after this whole process, this will become a 0 and this will be a 1. So now at least so this influence, the directed influence, you will track as an undirected influence with respect to this point. And the y over here will become a 1 and this will become a 0. Does that sort of make sense? Like if you had a 1, 0 and you applied this, then after switching, this becomes a 1. But in that ith dimension, you'll say, oh, what was the value before? And that value was 0. So there you're tracking that influence. So this influence gets tracked over here.
So that extra edge is not there in the cube. It's there to do the calculation.
It's there to do, yeah, but it basically appears, it appears over here. It will appear in this expression. So it's kind of left your primal and moved into the dual. And that's what you're tracking.
Thanks.
So essentially, you can boil all of this down to the following pretty simple combinatorial picture, which now we'll forget all of this notation. And we'll take 2 points. Again, we'll look at the x and y. Just ignore the ith dimension for now because that was a bit of a distraction. You've got a bunch of things here. You've got a bunch of things here. Some things here and some things here. Okay. And okay, so let's go ahead and actually put this in. And so imagine that these are all paired according to the ith dimension. So all paired according to the ith dimension. So I'm going to look at what I'll just call the inf of x plus the inf of y. Just standard square roots, right? So you look at any value that's a 1, you're only tracking influence there, and you look at how many things are zeros in these, and that's the influence. Now you go ahead and switch. So this is x and this is y. And you have some things here and you have some things here. And you're going to add this extra sort of hanging coordinate to just track whether the value changed there or not. But if this is bothering you, just even ignore that for now. And what you'll get is, I'll get inf prime of x plus inf prime of y. And what we need to show is that on switching, this is going to decrease. So let's see why that's going to happen. Okay. So let's just say, so there are a few cases. You basically have to work out a few cases. But case 1, I'm just going to draw out the cases. So this is 0, 1 initially. So all the influences are being counted here. So this is, let's say this is the red picture, right? So this is red. I'm looking at the red picture here. And here we're looking at the green picture here. So what I claim is actually the influence of y, because I'm looking at what's happening at y, is going to be greater than or equal to the influence prime of y. So it's even easier in this case. So, and this is just the property of the switching operator. So what's going to happen is that if there was any influence for y over here, that's because this value is a 0. But that means if you look at its partner value, that partner value would have also been 0 if you look at the same coordinate j. What that means is that no switch happened along this. which means that before switching also this must have been a 0. Right? It could not have been that this is a 1 and it becomes a 0.
Okay. So the ones above are the coordinates you have already the coordinates you've already switched on.
Actually, at this point, technically, this was actually looking at the influence on the primal.
Okay.
But the point is, at this point, the treatment of all of these coordinates is uniform. Like we're just treating them the same.
So it shouldn't matter, right? Because only the ith coordinate is changed. Only the switch on I should matter.
You're only switching on I. So in some sense, you can ignore everything and just say that I have these two stars.
If it's no, I think it's important that if you're switching on I, the ones before that, nothing happens. They stay. I mean, if they're not there, they're not there, right? I think that's important.
Sorry, say that again.
No, you're switching on I, then a non-monotone edge in the previous switched thing cannot become, or I mean the other way around.
Correct.
Monotone edge can't, so that's important, right? You're using it here.
Well, you're explicitly using that over here, exactly. But you're not using this in some other coordinate. You're just using it exactly over here, which is, as you said, you cannot create a non-monotonicity. But it's not even just you can't even create influence. Like if you look at a 1 which had a 0 associated with it, in this picture, if this was a 0 and this was a 1, then actually on switching, you're going to lose influence, which is even better for you. So the influence can only decrease on doing a switch. It cannot increase.
Yes. Influence may decrease, yeah.
It may decrease, but it's not going to increase.
Yes. The other one, it remains, I mean, it doesn't because switching on
the
one
other,
coordinate.
We're not even counting influences on value 0. Just to make life easy, just count influence on value 1.
No, that's true. But once you switch,
X and Y don't change.
Yeah, if it's 0, 1, it doesn't matter. I suppose if it's 1, 0, then you switch and then you have to worry about that, right?
So yeah, okay. So in case 2, if you're at a 1, 0, then it becomes a 0, 1. So technically what you will argue is that the influence of X is greater than or equal to the influence of Y, influence prime. So you have to like look at X over here and you have to track it in Y over here, right? So actually this is now going to get, so this influence over here is going to get tracked in this coordinate here, because this is that extra hanging coordinate. And everything else, if you look at any influence that 1 had before, it could only lose it. It cannot gain any influence. So let's just say, suppose there was a 0 here. Well, this other thing must have also been a 0, the partner, which means that if you look at the picture here, that was also a 0 to start off with. Is that picture clear?
Yes.
So there is no gaining influence in these settings. Again, this is the red and this is the green. The interesting case, which is really where now we're coming down to like where the square root is going to appear, is case 3. Suppose both values were 1, right? So now you have influence, you're tracking influence on both of these. Okay, now the picture is more complicated because things can gain influence. You don't have this sort of strict monotonicity that you had is not true anymore, because, for example, suppose you had a 1, 0 here. Now note that it switches and it gives you a 0, 1. So the influence has moved from here to here. The influence is moved from here to here. But what you see is that influence only moves leftward, which is, from y to x. So in this setting, what we'll actually see is that the influence of x plus the influence of y is equal to the influence prime of x plus the influence prime of y. In some sense, this is like, anything that was influential before, the zero is going to end up somewhere. Either it stays where it is or it switches. So if you look at a zero here, actually a zero here, for example, either it's going to stay there or it's going to potentially switch, which means that there is no losing influence anywhere. So this is where now one has to be worried that it could potentially gain influence. But what we can see is that any influence will only move, the zero will only move from the y part to the x part. The zeros only move this way. So because the zeros only move this way, what we can argue is eventually that the inf prime of x is going to be greater than equal to the maximum of the influence of x and the influence of y. So what you have is that because this influence only moves in one direction, the x will gain influence, and finally it is going to be greater than the max of these two. And hence, for any concave function, not just square root, what you get is you'll get square root of inf x plus square root of inf y is greater than equal to the square root of inf prime of x plus the square root of inf prime of y. But true for any concave function. So for any concave function, this is true. That essentially, right? Because essentially this is like a majorization argument. It says you have two terms here, x, y, the sum is the same, but in the right-hand side, the largest term is larger. And so the sum of square roots will decrease. And this is really where it boils down to. So in this case, you have to use the square roots. And so when you sort of trace this back, so remember this was the green picture here, and this was the red picture here. And so when you trace this back, this is exactly where we'll get that the red is greater than equal to the green, which is sort of this picture here. So we'll get the red is greater than equal to the green because of the square roots. And then that proves that this potential decreases. So when you put it all together, what we get is we prove this statement, that the directed is greater than the undirected version, but that gives you, it's greater than the variance of these gx's. Any questions at this point?
I think I'm good. Yeah.
And so finally, there is this step that the expectation of x of the variance of gx might be much, much smaller than the distance to monotonicity. But you can show that there exists a restriction. So actually it's a random restriction where the expectation of the variance of gx is at least omega epsilon f. So you have to be a little careful. There exists a restriction where this is true, and if you look at the distance to monotonicity of that restriction, that is also going to be large. So there are some arguments required here, but essentially you can apply all of this to a random restriction. And that's a bit of a technical argument. But once you put all of these pieces together, what you get is that you get this, or this is where the hard part is. You can show this is at least the distance to monotonicity, and then that proves the directed Talleyrand inequality here. Of course, there's an issue of robustness, which I did not get into. And then I've not told you actually the main result that we had, which was where you can generalize this for hypergrids. But I'm sort of at the end of time here, so I'll stop here and I'll take any questions that you have. Sorry, I had to rush a bit in the end, but yeah.
So thanks for the nice talk, Sheshadhri. Questions, people? So if not, I guess so, but I should check. Sundar, Piyush, Rohit, any questions?
No, thanks.
No, it's fine.
It's a bit intense, I admit. There's a lot of notational overload that one has to get over.
So I guess Sheshadhri, that's all. Thank you very much, and thanks to all of you for coming and giving this series of talks. We'll post it on.
Yeah, by all means, my pleasure. My pleasure.
Okay, thank you then. Thanks everyone, and yeah. So I guess goodbye.
Yeah. All right. Thanks a lot. Bye.
Hello.
Thank you.
Sheshadhri,
Yeah.
So I have a sort of general question. See, Talleyrand, suppose there are two posets, P1 and P2. So Talleyrand holds for P1, it holds for P2. Is it true that one can show it holds for P1 cross P2? I guess this is a key question everywhere, right? And is this known to be false? I suppose that's the right question I should be asking.
So, at some level, what we were doing in the hypergrids is really trying to pull that off, right? Where now you look at the hypergrid as some sort of product of lines.
Yeah, they're all products, right? This is also a product. That's also a product. And your proof seems to go, right, coordinate by coordinate. So it's as if you're doing so the proof is also, it uses the fact that they are products. So
yes, so
that's the reason why.
That's a good question. So actually what you need is for your base domain, you need some kind of operator that makes things monotone. Like you have the switch operator. In the line, you actually have something called the sort operator.
Yeah.
So you have to do everything that I described, where this S circ F means that you sort on those dimensions. And then you have to track all of these things, which we did a case analysis using a more sophisticated argument. But essentially the essence is that duality you can kind of preserve by saying that the dual are basically the coordinates that you're fixing. So in this example, if one had a sort of operator that for the base domains was making things monotone in some structured way, I think one may be able to pull it off. It's a very interesting question. I don't know if that answers your.
Yeah. So, for instance, I mean, take this itself. So the way, yeah.
Sorry, you're breaking up.
So that's your. Right. So that's. Yeah, I think the
sorry,
first thing to.
Sorry, Sundar, you broke up for a
first thing Yeah, no. So what I'm saying is the first thing to see is if I have some arbitrary posets P1 and P2, I have a switch operator for S1, I have one for S2. I apply first on S1, then on S2, then nothing happens to S1. I suppose that's the.
Yeah, you need that. Yes.
I mean, I'm saying this is for. I mean, this is your switch can be defined as whichever way you want to, but once you. So that is one thing you need. What else do you need? I mean.
So you need that.
And you only need that once you've done it for S1 and then S2, then it stays for S1 or something. Is there any other property that you really, really need?
Yeah, so you also need this fact that, like, in this switch operator, like the influence in that last argument, the influence is always moving from one thing to another. Because you need to minimize, you need to show the sum of square roots is reducing. So you need this majorization argument, which, for the line is actually pretty challenging to do. Like, even just if your basic posets were the line, that itself becomes a pretty non-trivial step to argue that, like, these sum of square roots are going to start going down.
I see.
So much so even just for the domain where, like, you take 3 to the d. Like, it's not immediately obvious. Like, you have to, and if you try the case analysis, it works. And then, like, how do you generalize the case analysis? So suppose, one were to say, like, do cliques. Let's say your base poset was some kind of directed clique, like a tournament or something. Maybe we could get things to work there. I think in a tournament it should work.
But that you've done, no? You've done the you've done.
That's true. We've done the lines.
You've done the line. Line is the same thing, right?
Yeah, line is the same thing. Yeah, you're right. Yeah. You know what? I'd be worried is there's like some sort of bottleneck in the poset, and like sort of everything has to go through that bottleneck. It's an interesting question, though. Yeah, I mean that. But yeah, one has to come up with that right sort of switching, the generalization of the switching operator. Any other questions?
Yeah, actually, just one more comment. I mean,
Yeah.
It's something that I mean, it doesn't worry me, but it sort of keeps nagging me all the time, which is see this distance from monotonicity, right? So it's something which how do I say this? So it's something to do with the transitive closure of the poset.
Mm-hmm.
You have a line, it's a clique, right, or whatever. On the other hand, the sort of left-hand side, the Talagrand whatever function, it just looks right above,
Yes.
a vertex. Yeah. So this is something that how does this sort of where and how does this sort of play a role? I don't know. So that's something that it's something that intrigues me. Let me put it that way. For instance, I could look up 2 levels, and now I can cook up a new sort of like a Talagrand objective. I can have a Sheshadhri objective, which looks up 2 levels and does something, right? Now, would that give you something more? Would that be?
At some level, isn't it a bit like, isoperimetry and you're defining, surface area and volume? So, like, to me, in a different aspect of that mystery is the fact that the distance to monotonicity.
Yeah, it's surface or area and volume, but you're saying that they are the same. So that's what bothers. Well, okay, there's a square root here. Okay.
Let me actually, it's kind of funny, but I'll give you a completely different angle to all of this, which it seems to be related to this, which is a much more natural question. It seems like what we were initially like some of our Margulis proofs actually work through routing arguments in the hypercube, which
Okay,
it
so
feels
that
like
I
what
can
this.
see that I can, I can sort of imagine that, right. So then you
Yeah,
can just look across up through influences and route it through influences, and then the sort of charging argument will be cleaner, I suppose.
exactly. So we struggled a lot to try to prove. So there's actually a very nice statement I can describe here. So let's just say you take two sets in the hypercube, both subsets of level sets. Okay, and let's just say that I have a matching between these sets according to containment, according to the partial order.
Yeah.
So I have A and above it is B, and there's a matching between them. And your job is to basically route from A to B, but I don't care how, but just route from the set A to the set B using vertex disjoint paths. So it turns out that actually this old argument of Lehman-Ron shows that you can do this. So meaning if you take A and you take B, then you can find vertex disjoint paths between A and B, assuming there is a matching between them. Now it seems like the further apart they are, the more vertex disjoint solutions you should be able to find. So can you find multiple vertex disjoint solutions that are mutually edge disjoint? So effectively it's like asking some kind of flow. Can you find a low congestion flow between those sets? And it seems that this, if you could prove a bound of that form, then you will prove Talleyrand. So
No, sorry. So just repeat it. So what do you mean by
okay.
So by flow? Yeah. What do you mean by? So these are not just edge disjoint paths or vertex disjoint paths.
Let me be more precise.
Yeah.
So you need to give me a flow where the edge congestion is 1.
Yes.
And the vertex congestion, okay. So I'm going to now, okay.
And
so
how much is the flow from a vertex to a vertex?
Exactly. So let me be more precise. So the simplest thing is to say, give me edge congestion 1, vertex congestion 1, which is just saying give me edge disjoint paths.
Yeah.
How many can you find? Well, I mean, just because they have to be vertex disjoint, it's just you can look at the cardinality of the set.
Yeah. So this is just symmetric chain decomposition, for instance, right?
Wait. How do you use the fact that the sets are matched?
Matched meaning if they are the same level, then there is right. If you get a symmetric chain decomposition of the hypercube, path goes from level I to n minus I.
Right, but I'm actually giving you two. I'm not necessarily using the symmetric chain decomposition to find those sets. I'm giving you two sets, A and B. And I'm just saying that I have a matching between A and B according to containment.
Okay, so you give me a matching and you want me to find edge disjoint. I mean, it's more than a symmetric SCD, right?
Yeah.
And that is a very special sort of matching.
Exactly, that's a special matching. I'm just giving you a matching, but I'm fudging a bit. I'm saying that you don't have to route according to my matching. I just want you to route from one set to another. So you're just doing, it's not multi-commodity, it's single commodity.
Oh, it's single commodity. Okay, so then what's wrong with SAD?
But how will you find? So if I just gave you two sets and told you this is the matching, the matching between those may not correspond to what you get from a symmetric chain decomposition.
Okay, so you can give me subsets. You're saying you can give me.
Yeah. I'm giving you subsets. Yeah, I'm giving you subsets of levels. Yeah.
Okay. Yeah, I got it.
So I give you subset of two levels, A, B. I give you this matching and I say you need to route from A to B.
Okay, so actually you can do it. I mean, okay. I mean, you can take an SCD and then you can, I think, work with, you basically take the automorphism of the cube and you route from the bottom up. You just, I mean, you use the automorphism to go from one to the other. I think you can do this.
Yeah, so there's also an argument by Lehman and Ron that we have a simplified, like you can use basically like some sort of, you can use Menger's theorem, like you can just do some induction and Menger's theorem and get it.
Yeah, you can do Menger's theorem also. Yeah, sure.
So it turns out that just from this, you can actually get some monotonicity tester.
I see.
Now,
So what is the other stronger statement you
the
wanted?
stronger statement is, okay, so suppose these sets are distance r apart.
Okay.
Now, the further they are, and assume that r is less than root n, everything is in the middle layers, just for simplicity.
Sure.
You would believe that somehow you should be able to do more. So now let me try to parameterize what that more is. I'm going to give you a flow problem. On every edge, the congestion is 1.
Yeah.
On every vertex, the congestion is r, where r was the distance.
Okay.
I want you to now route r times the set size.
Okay. Got it. Yeah. So Mhm.
If you can prove that statement,
Yeah.
I think the root D tester will also hold. And it seems to be related to this, but it's a little fuzzy. But I'll tell you what we can show. We struggle a lot. The only thing we can show is actually if r is equal to 2, then we have a proof. So what this says is you can actually route from A to B 2 times the set size with vertex congestion 2 and edge congestion 1.
Okay. Got it.
And we think that it actually holds for any r. So if your distance r apart, it's like saying that you want to find multiple edge disjoint paths or multiple vertex disjoint paths with some edge whatever. Like you basically want to flow.
So the source and destination, they don't have to be symmetric across the middle or something.
No.
Are they symmetric across the middle or no?
No.
Yeah, but I suppose if they are not, you could just go up. I mean, you can make them symmetric by making the smaller one bigger, right? But you'll have to go through this. Okay, it's not quite. Okay, I understand. I understand. Yeah, sure.
So this question seems to be related to a lot of these questions.
Okay.
And initially we had thought that would be an approach to prove it, which would be more like some kind of a charging, Menger's theorem, like, max flow min cut, that style of, but again, like we tried quite a bit on that, but I think we were missing the core ideas.
Okay, thanks. Actually, I need to go. There's an exam running and I...
Okay. Yeah.
But thanks for nice talks. Thank you.
Sure.
Bye.
Yeah.
So hope we can have more of these. Akash.
Yeah, I'm here.
Yeah.
Yes. Yeah. We'll try to organize that.
Yeah. Thanks, Akash. Yeah.
Thanks, Sheshadhri. Bye.